Okay, so we're talking about categorical predictors. Categorical predictors. I'm going to take a look at the iris data that comes with the base install of R. You can read the documentation. Let's see if you do question mark iris. There it is. It's Edgar Anderson's iris data, the famous, or Fisher's. I guess there's some sort of a dispute about that. Gives the measurements in centimeters of the variables sepal length and sepal width and petal length and petal width, respectively, for 50 flowers from each of 3 species of iris. Hey, in case you didn't know, the state flower of Tennessee is the iris. At least it used to be. Now I think it's not unique. I think there are several state flowers, but anyway, we have 3 different species of iris. We've got the setosa, we've got the versicolor, and the virginica. We've got 50 observations of each, making for 150 observations total. When we take a look at the head of this data set, you'll see we've got sepal length, sepal width, petal length, and petal width for each of these species. So, of course, we've got 5 variables there, and 4 of which are quantitative, continuous-ish, I guess maybe rounded to the nearest tenth of a centimeter. And then the species variable there is categorical, of course. I've just got the first 6 lines there. Now the petals are the flowery, pretty parts, and the sepals are the little green parts kind of things, I think, underneath the flowers. So maybe you want to check to see if, maybe you want to build a model for the petal size based on the sepal size or something like that for each of the different species. In case you didn't know, you can use the by command, by iris species applied to the iris data set. I want to get the summary. Okay, so what this will do is, well, just watch. See, well, it throws a bunch of errors at me, but for each species, it gives us some summary statistics for each variable. So for the species setosa, we have the 5-number summary, minimum, first quartile, median, third quartile, and the maximum, as well as the mean. So you get 6 statistics for each quantitative variable there within each categorical variable value. And you can see here, this is the species is the categorical variable. Under setosa, all 50 were of the setosa type, right? If I look to the versicolor section, it looks like, all 50 were of the versicolor type. And similarly, we have the output for the 50 virginica observations, and you see that all 50 of those were of the virginica type, right? Let's make a couple of graphs. First, I'm going to store some abbreviations. S will be for setosa, and little v for versicolor, and big V for virginica, okay? And I'm just going to, I'll use those to label my plots here in a minute. First thing, looks like I've just made some box plots, and I'm going to run them in the up-down direction. I usually like to see them running left-right, but for some reason, when I want to go and plot the means on there, it doesn't seem to work if I run them horizontally. But if I run them vertically like this, I can indeed plot the means there. That's what those blue balls are there. You can see that the means are not too far from the medians. Of course, this distribution looks a little bit right skewed right there, a little bit right skewed, and so the mean is going to be pulled up or to the right a little bit. Remember that the mean and the median can never be more than 1 standard deviation away from each other, so they aren't going to be too far anyway. Alrighty, let's plot, just for fun, sepal length versus sepal width. Okay, and if I do that, okay, I don't know, I see a bunch of dots there. Gosh, it would be nice if we could see how these 2 quantitative variables sort of interact with each other according to or by the species variable. So maybe what I'll do then is make the same kind of plot, except this time I'm going to label with those abbreviations I made. That's what this PCH equals as dot character of ABRV is for. And sure enough, might be easier though if they were shaped, more standard shapes like squares and circles and triangles, or if they were colored or something. But you can kind of see, look, here are all the S's down here, right? All the setosas are down here, and all the V's are sort of mixed up in with each other. It does look like maybe the little V's are sort of condensed here toward this region right in here. So it may be that it would make sense to build a linear model for the setosas. Maybe it would run right through here, and a linear model for the versicolors, and then a linear model for the virginicas. And then maybe you want to know, maybe a natural question would be, are the intercepts of those models the same or different? And are the slope coefficients for those models the same or different? Okay. All right. Well, what we want to do, though, is mainly focus on categorical predictors and how to handle those. So the categorical predictor here is, of course, there's only one in the data set, so it's going to be the species. First, let's take a look at, let's just pick one quantitative variable. Let's say sepal length. Sepal length. So I'm not going to look at sepal width right now. I'm just going to look at sepal length versus species, okay? Sepal length versus species. I'm going to do analysis of variance and store that output in AOV.out, okay? And take a look at the summary. Now, one thing you should always do when you run the AOV command in R is double check your degrees of freedom, because, let's see, did it do it right? Yes. Okay, we had 150 observations. Take away 3 for the total degrees of freedom for the residuals there. That's because we have 1, 2, 3 different species, or you can think of the species as sort of a treatment variable there. Okay, also the number of degrees of freedom for species is going to be the number of species minus 1, right? So 3 minus 1 is 2. So that looks correct. Where this can go wrong is if, for example, your categorical variable is somehow treated as a numeric quantity, and it can then assign the wrong degrees of freedom there for it. It would maybe say the degrees of freedom for your model then would be 1, okay? And then everything else is all messed up, and you get incorrect p-values and all kinds of stuff. So, but it looks like everything's okay. So yeah, again, I'm just going to check the class on that species variable just to make sure. It should be a factor class, and it's R just doesn't like me tonight. I don't know what's going on, but it's a factor class. Looks pretty good to me. Okay, I think we're all good there. Okay. Now, at this point, we could run some post hoc tests to investigate the exact relationships between the group means. Remember that analysis of variance is really a pretty weak test. All it does is it tests, the null hypothesis is that all means are equal versus the alternative that at least one of these things is not like the other, right? At least one mean differs from the rest, okay? If you get a small p-value in ANOVA, it just tells you that at least one of those things is not like the others. It doesn't tell you which one. It doesn't tell you which ones. It doesn't tell you if if the top 2 means are about the same and the bottom 3 are about the same or something like that. All that stuff can be checked with post hoc tests, okay? If you don't know anything about that, you can find them in the Ott and Longnecker book. They're in most basic statistics books, and they are all over the web. So enough on that. Let's take a look at Bonferroni intervals, 95% Bonferroni intervals. That is, maybe I want to be, 95% confident that we catch all these parameters at the same time, right, in their respective intervals. Well, in that case, I need to make the Bonferroni adjustment, right? 95% family-wise error rate, so 1 minus that is going to be 5%. Divide that by the number of intervals I want to make, which is 3, and then take that much off of 1, okay? So that's, that's going to be 98.3 repeating percent, okay? So what I can do is I can just feed the ANOVA output to the conf_int function and tell it that I want to use this level. BL is what I've called it, for Bonferroni level, and take a look at that. Looks like, let me do that again so that I get it all together there. So yeah, so these are, so each one of these intervals is a 98.3 repeating percent interval, but all of them together they are Bonferroni 95% intervals. That is, we can be about 95% confident that the actual, what is this? What was the mean for Setosa? It was, let me just see there. Setosa mean was the lowest one, 5.006. That's smack in the middle of this interval. This is a 98.3 repeating percent confidence interval for the actual Setosa mean sepal length. Well, that's a mouthful. This has something to do, this is some kind of interval for versicolor. But look, the versicolor mean is more than the Setosa mean, and this is something to do with the Virginica mean. But this is the Virginica mean. It doesn't fall in between there and there. Okay, this is what R does. It'll set one of those categorical variable values, in this case Setosa, to be sort of the reference level. Okay, so in this case, Setosa, that's our reference level. Okay, so that's going to estimate, this gives me a confidence interval for that mean, for the mean sepal length. This then is a confidence interval for the effect off of this mean that it takes you to get to this. So see, watch this. Let me take this interval. This is a confidence interval for the adjustment that you have to make to the Setosa mean, okay, to get to the versicolor mean estimate. Okay, what am I doing here? I have no idea. Let's see. I'm going to average those two numbers, and there we go. This 0.93 is a point estimate for the effect of changing species from Setosa to versicolor. Okay, so that is if I take the Setosa mean, 5.006, and if I add that 0.93, guess what I get? I get the versicolor mean right there. And guess what? If I take this confidence interval, remember, for these kinds of confidence intervals, these T intervals, the point estimate's always going to be right smack in the middle of the interval. So if I average those two interval endpoints, that gets me, okay, that is the point estimate for the effect of changing species from Setosa now to Virginica. Okay, these two are, they both pivot off of sort of this point here. Okay, so if I take 5.006 plus 1.582, guess what? We're going to get this 6.588. Cross your fingers and stand on one foot. There it is. Yes, perfect. It works out. So that's how R naturally gives the output. You need to be aware of that, or you won't read it right. Let's see. I can get the coefficients for ANOVA. Okay, if I remember this str command, str of say AOV.out, real handy dandy command there. It tells you everything that's in that AOV.out stuff, that ANOVA output, and so there you can extract all kinds of things there. If I take a look at the coefficients, there they are. This is just the intercept itself, which is, again, in this case, it's an estimate for the Setosa mean. It's the intercept. It's the bias value up off of 0 that you have to add to get to the mean of the mean sepal length of Setosa. And then add this much to this, and you get the versicolor mean. Okay, which was that. And if you add this much to this, then you get the Virginica mean, right? That's what that was. Remember, M contained my means. So yeah, those are the actual means. Okay, so let's make some dummy variables, shall we? Remember, we talked about dummy variables. The idea being maybe D1 is, say, 1 if the species is Setosa and 0 if it's not. And maybe D2 is going to be 1 if the species is versicolor and 0 if not. And D3 will be 1 if the species is Virginica and 0 if not. So let's define those. And you can see, the first one, this is D1. All I've done then is I've just put 1s in the first 50 spaces and then a whole bunch of 0s, right? So that's exactly what that variable is. Okay, this is signaling species. The first dummy variable there is signaling the Setosa species. Okay, and the second group of 50, Those were the Virginica, no, sorry, the versicolors, right? Yeah, so that's what that's signaling, and D3 is signaling the Virginica species, okay? Now, what I can try to do here is, let's build a linear model of sepal length versus just these binary variables of the iris data, okay? Let's see. Didn't build it. There we go. Build the model. Load the Fairway library because maybe I just want to use the 1M summary command. Again, that's just a little streamlined summary there. All right, so here are my estimates. Holy smokes, what is that? 6.588? Oh, what's this error? Coefficients. One not defined because of singularities. Okay, this doesn't mean the number 1 is undefined. What this means is that one of the coefficients is not defined because of the singularities. There's an invertibility issue that we'll address in just a minute, but notice right now that in fact we only have estimates for D1 and D2 and not for D3. Why is that? Well, because one of those species is taken to be the reference level, okay? It's not Setosa this time. Which one is it? Let's check our means. What was M? Okay, it looks like it's this one. It's the Virginica mean, 6.588, 6.588. So this case, R has taken Virginica to be the reference, and you can check that if you look back at your box plots. Yeah, indeed, you know, the blue ball here in the Virginica aisle there, that's 6.5 something or other, okay? And then what this says is that to get down to Setosa, I guess, remember D1 signals the Setosa species, right? Setosa for D1. You start here at the 6.588 number and go down, negative means down, go down 1.582, okay, to get to the mean for Setosa, which would be here, okay? So start here and go down that much to get there. And to get to the mean for, what's the other one? Versicolor. I start here and go down, negative means down, go down 0.652. And that, so I start here and I go down, it takes me down here to the versicolor mean, okay? These are standard errors. These are standard errors for these estimates, so you could make confidence intervals for them that way. What's this finding? It looks like all these p-values are pretty darn small, indicating that, yeah, in fact, there does seem to be a difference. Now, keep in mind, we're only looking at just one categorical variable and one quantitative response here, right? We're not looking at this case over here in the far right plot where we have 1, 2 quantitative variables and a categorical one. We might do that later on, okay? In fact, we will do that later on. We will mix categorical and quantitative predictors together to build models to predict a quantitative response. Yeah, so, and don't forget, you can, of course, you can run the 2M summary and get more information. R squared has the same meaning as it always has. It's the proportion of variation in the response that's accounted for by your model. That's what that is. The F statistic, this is your ANOVA F statistic. Okay, it's on 2 and 147 degrees of freedom. Remember, 2 treatment degrees of freedom, or between groups degrees of freedom, 147 residual degrees of freedom. Okay, the p-value is tiny. This is just checking to see if there's a difference in the treatment means, and it certainly seems to be finding that. Now, what's this invertibility issue I warned you about? Well, let's get my model matrix. Okay, I can do that with the model.matrix command. I'll store it in MM. Take a look at this. What do you see? It makes sense that this is what it ought to be. I've got one, the first column is just a bunch of ones to pick up the bias term, okay? And then the second column is 50 ones and then 100 zeros. And then the third column is a bunch of zeros and ones and zeros. And then the fourth column is 100 zeros and then 50 ones to trigger the Virginica species, okay? So yeah, so let's do this. What I'm gonna do is I'm just gonna store my sepal links there in Y, okay? That's all I'm doing. And then take a look at Y. Yeah, it's 150 by 1, so it's got 150 rows. It's It's a column vector. Okay, good. It's of matrix class. That's good. Now, remember, our least squares coefficients are found the same way by finding x transpose x. This is our model matrix. M is our x here. X transpose times x quantity inverse times x transpose, and then it should be times y. For some reason it's missing, but I'll stick it in there. Okay, and whoa, lo and behold, the system is computationally singular. Okay, reciprocal condition number equals something tiny. Okay, it's not just computationally singular, it's absolutely singular. Okay, how do I know this? Well, because, now by singular, remember we mean non-invertible. Take a look at this. These columns in our model matrix are not linearly independent, and I know that because, look, what if I sum the second and the third and the fourth columns? That'll give me the first, right? If I, add, say, this plus this plus this, I get 1. If I add this plus this plus this, I get 1. See what I mean? And, similarly, where we go? Add this plus this plus this, I get 1, okay? The columns are not linearly independent. So we have an invertibility issue. This model is what we might say overdetermined. D1 is going to be 1 if and only if D2 equals D3 equals 0. So one of these three columns can be eliminated, okay? Any one of them. And so that's what R has done. It looks like it has thrown out, I guess, was it the first one? Now let's eliminate D3. Okay, so I'm going to do, let's see, I'm going to call it lmod.nd3. That's for linear model dot no D3. Okay, yeah, so notice that I had a typo here. It looks like it was just lmod. That would give me the wrong thing, right? So I'm going to do like so, and there we go. Okay, now I don't get that error that we got before about singularities, right? This is our estimate for the mean sepal length for the Virginica species. This is the estimate for the effect to get from that reference mean down to Setosa, and then this is the estimate for the effect to get from the Virginica sepal length mean down to that of the versicolor. Okay, you can alternatively just eliminate the intercept. Okay, you can do it this way. I'm going to call this lmod.noint for no intercept. Linear model sepal length versus D1 plus D2 plus D3 minus 1. This is the funny little notation. If you put that into your model, it tells R not to fit an intercept. Okay, not to fit an intercept. So watch what happens when we do that. Yeah, in this case, our model matrix is just the last three columns, right? You don't have a column of all ones. And now, if I take a look at the summary, you'll see we get the actual means, okay? The actual treatment means or species means. We don't have to think too hard. We don't have to deviate off of them. But this is, while it's useful in that regard, it's not as useful because t-test, checking for the significance of the means, they're checking to see if the category means are statistically significantly different from 0, okay, which of course they are, okay. What we'd probably be more interested in is maybe checking to see if maybe one of them is different from 0, and then maybe simultaneously are the other two different from that one, okay. This output doesn't tell you about that, okay, so that's why the default in R is the way it is, okay. So let's see, yeah, so typically, do not omit the intercept term. Instead, leave out one of the indicator or dummy variables. How many do you leave out? Well, it's like this. If you have a categorical variable, okay, and it has, say, T levels, T, say, number of treatments, then need T minus 1 dummy variables, okay, and that's it. Okay. Otherwise, if you go more than that, it'll be overdetermined. You can't invert the matrices and all kinds of bad stuff happens. Okay. So that's what you do. What happens if you have more than one categorical variable? Well, that's fine. If you have one categorical variable with 3 levels and another one with 5, then maybe you need 3 minus 1 is 2 dummy variables for the first categorical, and 5 minus 1 equals 4 dummy variables for the second. Now, R will do all this automatically for you. I'm going to call this output lmod.new. lmod.new. So lm, here's my quantitative response versus species. Watch what happens. I don't actually have to define those dummy variables. I don't have to do that. Do that, and summary, check that out. Look, it does it for me. It does it for me. Now it gives the output in the same format that we're now getting used to. One of those levels has been treated as a reference level. It's obviously the Setosa one, and then I can tell then that this is the effect to get off of the Setosa mean to bring it up to the versicolor mean estimate. I add 0.93 to it, and then similarly here for the Virginica species. Okay, but notice I didn't have to define any dummy variables for that. It'll take care of all that automatically. And again, just checking that species is of factor class. Sometimes it might make more sense to force a different reference level. For example, if you had, say, 3 treatment groups or 5 treatment groups, whatever. Maybe one of the treatment groups is a control group where you do nothing, okay? You're giving people placebo or 0 level of active ingredient, okay? And then group number 2 gets 5 milligrams, group number 3 gets 10 milligrams, group number 4 gets 15, and group number 5 gets 1,000,000 or whatever. It might make sense to force a different reference level, make the reference level in that case, set that to be the control group. You can do this with the relevel command, but you do this on the data set itself. Okay, so relevel iris species. Okay, I'm just going to relevel just that one variable. Reference level I'm going to set to versicolor. Maybe we want that one to be the reference level for some reason. I think it actually makes a lot of sense to, I mean, I don't know the first thing about irises except that, you know, I like them and stuff. To me, it sort of makes sense just looking at the plots here that Setosa it might be nice to set as the reference level because it's lowest, you know, and then I can add a positive amount to get to versicolor from there, and then add another positive amount from Setosa to get up to the mean for Virginica. Okay, so that sort of makes sense. But if for some reason I wanted to set, I don't know, versicolor as the reference level, I could do it this way. And you can see that that's sort of what R is indicating, that variable, that categorical variable, has 3 levels, but now we've set the reference level there is versicolor. That's what that last line of the output is for. Okay, so now if I make lmod new.to, okay, sepal length versus species, same command and stuff, then take a look at the summary for that. You'll see, in fact, it doesn't tell you what the intercept is for, but you can tell by process of elimination, right? This is for species Setosa, this is for species Virginica, so this one must be for the versicolor species. That's estimating, this is the sample mean for the versicolor group, right? 5.936, that's right there, that blue dot right there. And then to get to the Setosa mean, I come down from that by 0.93, right? Start here, come down 0.93. Or to get to the Virginica mean, you start here and go up by, what was it? 0.652, okay? Similarly, you know, you could, if you wanted to, you could set, what is this? Set it back to Setosa. Yeah, do whatever you like there.